Hi, hello everyone. Welcome back to LFI Educates. Today we are going to start this chapter, Current Electricity, that is chapter 3. To start with, first of all, we need to know about electric current. Electric current. When we say electric current, it is the rate of flow of charge across any cross section of the wire, or we can say that electric current is the quantity of charge that is transferred per unit time across the wire of certain area of cross section or unit area of cross section. Current is indicated by this symbol I, capital I. This indicates electric current. Q here indicates the total charge, and T indicates time. Now, all the time, it is not necessary that the current will be steady. If the current is not steady, if it is varying, it is changing, sometimes it is becoming more, sometimes it is becoming less. It happens generally when we study alternating current. So in that case, the expression for current can be written in the limit form, limit delta t tends to 0, delta q, delta t. This way also we can represent electric current. And if you want to write in differential form, ddt of I, or you can read it as di dt. So this is in more general, you can express electric current. The SI unit of electric current is ampere. It is one of the basic unit that is accepted by SI system, that is System International. SI unit of electric current is ampere. We say that 1 ampere of current is flowing through a conductor of unit cross section when 1 coulomb of charge flows for 1 second. Then the current, we call it as 1 ampere. So 1 ampere, you look the formula, the current 1 ampere, when you write, it is 1 coulomb of charge that flows per second. That is the SI unit of electric current. The next thing you'll have to know here is about current density. We represent it with capital letter J. Current density, here it indicates the concentration of charges, or we can say current density J is equal to the amount of current per unit area of the conductor. The amount of current per unit area of the conductor, we call it as current density. Its unit is ampere per meter square. This I here indicates current, and A here indicates area. So the unit will be ampere per meter square. In short, you can write it as capital A, that will indicate ampere, and per meter square. That is about your current density. Then let us see today about the first law that you come across in electricity, that we call it as Ohm's law. George Simon Ohm in 1927 gave us the relationship between potential difference across the ends of the conductor, the electric current I, and the resistance R of the conductor. And this law, when you study throughout electricity and electronics, this law is applicable. It's a very important law. It states like this: the total current that flows across any conductor is always directly proportional to the potential difference between the two ends of the conductor, provided the physical condition of the conductor remains the same. Here physical condition indicates mechanical strain, stress, temperature, pressure, etc., etc. If the physical conditions will remain the same, then only the law is applicable under that condition. It says like this: the potential and current, the potential difference and electric current are always proportional to each other directly. If the potential difference will increase, then the amount of current also will become more. And if the potential difference decreases, the amount of current also becomes less, it decreases. To express mathematically, V is proportional to I. We write this as V. When you remove the proportional sign, the constant term here, R, is called the resistance of the conductor, R into I. Or we can write this as V by I. V by I is always constant. Here R is constant. As I said, R is the resistance of the conductor. So these two ratio always will remain the same. Then we call it as Ohm's law. And this gives us the relation between potential difference, electric current and resistance. Ohm's law, as we studied, V by I is equal to R. This is constant. Now this, what does it mean that R is constant? Resistance is constant. This one to know, let us do one small activity. Suppose these are the two ends where you are going to fix a material to know its resistance. We will connect one ammeter here. At these two ends, we will connect one voltmeter. Then we will take one key, a battery or a source of electricity, then one rehosted. This way you have to do the connection. This is your variable resistor, we call it as rehosted. Let me write it as RH. You have to be very sure that the positive terminal is connected to positive terminal of the emitter, and the other end will be negative. This side will connect it to positive and this one will be negative. Ammeter is an instrument to measure electric current, and voltmeter is an instrument to measure potential difference. Suppose I want to know the potential difference between the two ends A and B, then I will connect voltmeter in parallel with AB, one above the other, and this is in series. Ammeter is connected in series with the conductor that I want to know the resistance. Let me take the conductor like this. AB is a wire. I want to know the resistance. In this circuit arrangement or the circuit diagram, we call it as Ohm's law circuit. What we do is, first of all, we adjust the rehostat. We make a small table to find out the values of V and I. First of all, this pointer, if I move it towards my right, if I keep it here, you can slide the pointer. You slide, in actual practice, it is a clip on top of the long wire. If you slide the wire, we can increase and decrease the resistance. When I slide it this side, then the resistance will become more. Current is flowing this way from positive terminal. This way it is coming. So here the current has to come up, down, up, down, up, down. It will offer more resistance. Then with great difficulty only it will reach here. Here the resistance is very high. When the rehostat resistance is very high, then the amount of current here will be very, very less. And if amount of current is less, the voltage also should become less according to Ohm's law, that V is directly proportional to I. Now, to start the experiment, you'll do like this. First, you adjust the rheostat. Suppose I want to make very high resistance. From high to low, I am trying to do. So I'll place the pointer towards my far right, and then I'll switch on the switch. This is your switch. When you close the circuit, means switched on now. Switched on means close the path. Then current will start to flow through emitter as well as through voltmeter, through this wire, and then it will come down along the rheostat and will complete the circuit. Now, as soon as I switch it on, I can see the pointer in emitter and voltmeter readings. In emitter, if I see that the current is 1 ampere, because the resistance is very high, suppose it is in ampere, suppose, then ampere will generally write it as capital letter A. 1 ampere, then there will be some potential difference. Let us say that it is 4 volt. It is in volt. Now I will switch it off. That means I will open the circuit, current flow will stop, the pointer will come back to 0. Both the pointers, it starts from 0, 1, 2, 3, 4, the scale is like this. There will be one pointer, it will fall back to 0. Then what I will do is, I will hold this rheostat and then I will slide it a little bit towards my left. Now in this case, you can see the resistance is a little bit less. Now when the resistance is less, automatically the amount of current will increase. Then voltmeter also will show more reading. The potential difference between the 2 amps will become more according to Ohm's law. Let us do and see. Switch it on, then take the readings from emitter and voltmeter. Suppose this time the emitter reading is showing as 4 ampere. Then if you look at the voltmeter, then automatically that also will increase from 4 will increase to 16, say. Like this it will go on changing. Numerically always the potential difference numerical value is more than the current. Like in our home we get 220 volt of electricity, but the current is around 5 ampere only. But they are directly proportional. If current will increase, potential difference also will increase. If current will decrease, potential difference also will decrease its value. But numerically, this value numerical wise, potential difference is always more than electric current. Now again, let me switch it off. Let's open the circuit, current flow will stop. Again it will fall back like this to 0, both the readings. Then what I will do is, I will bring the rheostat this side, I will make the resistance very, very less. And again if you switch it on, again take the readings, not on the readings of voltmeter and ammeter. Suppose this time it has become 8, the current reading shown by the ammeter. Potential difference reading, it will be suppose 32. Like that, if current is increased, the potential difference also will increase. Now if you calculate the value of V by I, that will give us the resistance V by I. In the first case, if you calculate it, it will be 4 by 1, it is 4. If I calculate V by I in the second case, 16 by 4, this is also 4, this will be ohm, this also will be ohm, we are calculating the resistance. The third case also, if you find the value of V by I, 32 by 8, it will be 4 ohm. So we can say that this wire which I have fixed up here at A and B, this wire has a resistance of 4 ohm. Whatever may be the value of current and potential difference, the ratio always will remain the same. That is the meaning of the constant term. Now these values, if you plot it graphically, V versus I, V along x-axis and current I along y-axis. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Like this, if you go on plotting, this side also 1 ampere, 2 ampere, 3 ampere, 4 ampere, 5 ampere, 6 ampere, 7 ampere. This one I am going to change it now because it has become too long. To get up to 32, I will have to go across the tables. So what you can do is, you can do like this. You can change the scale. First 1 centimeter, you can take it as 5, 10, 15, 20, 25, 30, 35, 40. Like that you can take them here. From here to here there are 10 divisions. 0 to 5 there are 10 divisions. Like this. The 0 marking, this is 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is the 10th line. So if I go 1, 2 step, then it will be counted as 1. Another 2 step, then it will be counted as 2. This is 3, this is 4, and after this 2 it will be 5. So now let me plot it. Current is 1 ampere, when potential difference is 4 volt. It will be near to 5, this one 4 volt. Then current is 1 ampere. This is 1 ampere. Then the second case, when current is 4 ampere, here the current potential difference is 16 volt, 15, 16, then 2 marking will go this way. Then current is 4 ampere. Like this to come here, you plot it, and then when it is 32, potential difference is 32, 30, this is 31, this is 32. Then current is 8 ampere, 7, this is 8. Like this will come. So if you join all these points, you will get an incline, straight line starting from the origin. So this verifies Ohm's law. Now what is resistance? That also you have to learn. Resistance is the property of a conductor to oppose the flow of electric current. It is the property of a conductor. Any metallic conductor, if you allow current to flow through it, it will offer resistance. Some materials, they may offer less resistance. Some materials, they may offer more resistance, but it will offer resistance. Let us take some examples like silver. We know that is the best conductor of electricity. So currents will flow very nicely through silver. But even though it is the best conductor, it resists little bit. Resistance is present. It also resists electric current. When we talk about nichrome, that is the, how to say, worst conductor of electricity. It offers maximum resistance. The amount of resistance offered is more. So like that, some materials, they may offer less resistance, some may offer more resistance, but it will offer resistance. That we can come to know when we are using an electric iron. Suppose if you are ironing our clothes, sometimes the insulated wire, if you just hold it and see, you will come to know that, oh, it's becoming hot. So from there you will come to know that the wire inside is offering resistance. So whenever resistance is offered by the wire, then the wire will automatically become hot. That we call it as heating effect of electric current. Later we shall study about that as well. Now about resistance. As I said, it's a property of a conductor to offer or to oppose the flow of electric current, or you can even say flow of electric charges. It offers or opposes the flow of electric charges. Now, the materials which offer resistance, we call them as resistors. We call them as resistors. Like as I said, silver, nichrome, tungsten, any metal you can take, iron, aluminum, they will be called as resistors. So because they offer resistance. Now this resistance is found to depend upon some following factors. Now let me write down one by one. Resistance depends upon its length. Resistance depends upon its length. But how does it depend? Then we'll say that it depends directly. It depends directly. Longer the length of the conductor, the resistance offered will be more. Let me draw and show you here. Suppose two wires I have taken. you can see one wire. This is the other wire of same area of cross section, that means same thickness. Then wire A is longer in length than wire B. So automatically, if you follow this, resistance is directly proportional to length. You will say that wire A will offer more resistance than wire B. But you have to keep in mind that the thickness must be same in both the cases. Secondly, let us see on what factor it depends. It depends upon the thickness, or we call it as area of cross section. Then we write it as A. How does it depend? Then resistance depends inversely with the area of cross section 1 by A. If the area of cross section is more, the resistance will be less, and if the area of cross section is less, then the resistance will be more. One side increasing, then the other side must decrease. To know this, let me draw here two wires of same length. Here you have to focus like this. Suppose this is wire A. Both are of same length, then only it is applicable. If both are of same length but of different thickness, one is more thicker, this is your area of cross section, is more in wire A, so resistance offered by this fat wire, the thick wire, will be less because area of cross section is bigger. Then the third factor on which resistance depends, nature of the wire. Nature of the wire, or nature of the conductor, or you can say nature of the material. Whatever you say, the meaning is the same. Let us see about nature of the wire. As I gave you the example earlier that silver and nichrome, if you compare, nichrome offers more resistance. Silver, being the best conductor, offers the least resistance. Now, so both this silver and nichrome, both are metals, but they have different properties. Their natures are different. That's why the resistance offered by them are also different. And lastly, the fourth factor on which resistance depends is temperature. It depends upon temperature. This temperature, when you increase in metals, then the resistance also will become more. It is directly proportional for metals, remember this. But for insulators and semiconductors, the reverse thing will happen. If you increase the temperature, the resistance will become less. The resistance will become less. And for alloys, mixture of two or more than two metals and a non-metal, that we call it as alloy. In case of alloy, the resistance will be very, very less. If you increase the temperature, if you go on increasing the temperature, the resistance is very, very less. Let us discuss this about the dependence of temperature on resistance. Here mathematically, we can learn like this: temperature dependence on resistors or resistance. Mathematically, we represent like this: resistance at any temperature T is equal to R naught, that is the initial resistance, multiplied by 1 plus alpha delta T. Delta T is the change in temperature. You can even write final temperature. I can write T final, that is at temperature T, minus initial temperature T naught. Like this also you can write down. Here if you rearrange them, RT divided by R naught is equal to 1 plus alpha T minus T naught RT by R naught minus 1 is plus I'm bringing here. So alpha, let us write this as delta T. This is a change in temperature. So here if you take LCM, you will get like this, R naught equal to alpha delta T. This can be written as alpha is equal to RT minus R naught divided by R naught into delta T. You may be wondering here, what is RT and what is R naught? T and naught is used for what? Then you should know that T naught is the initial temperature. Whenever I'm writing T naught at that initial temperature, what is the resistance? Then R naught. It's like this. At T is equal to T naught, resistance we are taking it as R naught, and at T is equal to TT, R we are taking it as resistance, we are taking it as RT. Suppose the initial temperature is 20 degrees Celsius. That means the resistance at that temperature will be the resistance at 20 degrees Celsius. Final temperature, you have applied heat, suppose, or we allow current to flow through the wire. Then it will become hot. Suppose it has become 40 degrees Celsius. That's an example I am taking. So temperature is suppose 40 degrees Celsius. Then that means at this temperature 40 degrees Celsius, the resistance is written as RT. RT is the final and R naught is the initial resistance. Then what about this alpha? Alpha is called the coefficient of resistance. Coefficient of resistance. Here alpha is called coefficient of resistance. This coefficient of resistance, how we can define it now? Can define from this formula. The coefficient of resistance is defined as the change in resistance per original resistance R naught initially before heating per change in temperature. Like this we can define it. The change in resistance per original resistance per temperature change, unit temperature change, delta T. You can define it this way. And what does it tell us? This alpha value, if you calculate, two, three things you will come to know. If the value of alpha is positive, if alpha is positive, then you will come to know that, that the metal, the object we are talking is about metals. For metals, the value of alpha is always positive. For semiconductors and insulators, the alpha value is negative. The alpha value is negative. This is for semiconductors and insulators. Whereas in case of alloys, the value of alpha is very, very small. Very small. Very small. If I say it will go beyond this, that means it has less dependence. Resistance depends very slightly on temperature in case of alloys. In case of alloys. Now, when we study about resistance, there is another very important thing to know along with it. That is your resistivity. Now let us see what is resistivity. Or we call it as specific resistance. We denote it with this symbol rho. It's a Greek letter. Rho indicates resistivity, or we call it as specific resistance. Now to get the expression for specific resistance, we'll use the first two factors that we use in resistance. Resistance, we know that is directly proportional to the length of the conductor. Let us make it as equation number 1. And also we know that it is inversely proportional to the area of cross section of the conductor. This is 1 by A. Let us take it as equation number 2. When we combine these two factors from equation 1 and 2, we can write resistance is proportional to these two, multiply it, L into 1 by A. You'll get R is proportional to L by A. Now to remove this proportional sign, we use a constant. That constant term we call it as resistivity. We write it as rho L by A. Or if you want to know the expression for resistivity, then simply cross multiply. Rho is equal to R times A by L. This gives us the expression for resistivity. And it is defined as the resistance of the conductor. Resistivity is equal to the resistance of the conductor if the conductor has unit area of cross section. Unit means what? 1 meter square cross sectional area, and the length of the conductor is exactly 1 meter. So if a conductor of length 1 meter and area of cross section 1 meter square, how much resistance this conductor offers, that we call it as resistivity. That is the definition of resistivity. But in general, how you have to know is, what is resistivity? If your friend asks you, or any person from outside, if they ask you, they have not gone to any science class suppose, then you should be able to say that resistivity is the capability. Resistivity is the capability of the conductor to offer resistance. That we call it as resistivity. In a simple language, if you say. But if you define it scientifically in a physics way, then you define it this way. Resistivity is equal to resistance of the conductor if the conductor is of 1 meter square area of cross section and the length of the conductor is 1 meter. Now, let us talk about the units. What about resistance? When we talk about the units, resistance unit, you know, it is given after a German physicist. Who was that? George Simon Ohm. So, unit of resistance. Resistance is R. Unit is ohm. Symbolically, we write it as omega. This is a symbol for ohm. These are the SI units. I am talking about the SI unit of resistance. Then what about this? Resistance is ohm. Area of cross section is meter square. Here resistance is ohm. Area of cross section is meter square. And length is meter. All SI unit, if you use 1 meter, if you cancel it from numerator and denominator, then you get the unit for resistivity, that is ohm meter. So SI unit of resistivity, rho, is ohm meter. Or in short, we write it as ohm meter. Like this, we represent the unit for resistivity and resistance. Now you may be interested in what factors this resistivity depends. Actually, resistivity depends only on the nature of the substance or nature of the wire, and it depends upon temperature. It depends upon temperature. How it depends upon temperature? Then you can see here. I'll show you. This resistance, if you just all remove it with resistivity, then you get the expression for it. And just I'll show you. Temperature dependence on resistivity. just this R, you make it as rho. Simply this R, you make it as rho. Little bit pull it down, it will become rho. Like this, like this. Bus, and then you'll get the expression for temperature dependence on resistivity. Here alpha will be called as coefficient of, instead of resistance, we'll call it as resistivity, and it is defined as the change in resistivity per unit portional resistivity per change in temperature. And what about the units of coefficient of resistivity, coefficient of resistance? Their units also you have to know. Here you can see the resistivity unit, whatever you write ohm meter, this is also ohm meter, it will get cancelled. And SI unit of temperature is Kelvin, so it will be per Kelvin. SI unit will be per Kelvin. K indicates here Kelvin. The same way, coefficient of resistance also the unit is same. It will be per Kelvin. Now let us do some few numericals and then see what are things we have discussed. Let us solve some few simple numericals. Let us see the first question. Question number 1. Solution. How many electrons? The moment they say how many electrons, then they are asking number of electrons that we come to know. We represent it with small letter N. How many electrons pass through a lamp in 1 minute? Time is given to us, so write time T is 1 minute. 1 minute is equal to 60 seconds. We have to convert in SI system. The SI unit of time is second. If the current is 300 milliampere, so current is given, current I, let me write, this is 300 milliampere, milli means 10 to the power minus 3 ampere, we convert it into SI unit of current is ampere. Given the charge on an electron is, as you know, the basic unit of charge on an electron E is given as 1.6 into 10 to the power minus 19 coulomb. Write down the given information is this way, and after that, what to find number of electrons? Number of electrons. Let us write it as N. So we are going to calculate. So now, as current is given, you already know that electric current is the quantity of charge transferred per unit time. You can start like this. We know that, or as per question, current I is equal to charge per unit time. But here, number of electrons does not appear. So use your quantization condition of charge. I is equal to Q is N into E divided by T. Then basic unit of charge you know, time, how long is flowing through the lamp you know, current value also you know, so you can find out N. To find out N, it will be I into T divided by E. Then place the values. N is equal to I into T. The current is 300 into 10 to the power minus 3 ampere. All an SI unit, you don't have to mention the unit there. Time, it is 60 seconds divided by the basic unit of charge 1.6 into 10 to the power minus 19. Then if you calculate, you will get your result. 6 3s are 18 into 1, 10 power minus 3, and here 10 power 3. So it will become 10 power minus 3 plus 3. It will give us 10 to the power 0. Any number raised to the power 0 is 1. Then downside you have 1.6. If I write 16 after decimal 1 digit, if I remove it on a numerator, multiply by 10. And this 10 power minus 19, if I take it up, it will become 10 to the power plus 19. Now you can divide it. 2 8s are 16, 2 9s are 18, 9 by 8, divide it 9 by 8, 8 1s are 8, 1 0, 8 1, sorry, decimal, and 8 1s are 8, 2 0, 8 2s are 16, and so on. After decimal 1 digit, if you get, is good enough. 1 2 into 10 to the power 19 plus 1 is 20. So the number of electrons that is flowing through the lamp will be 1.12 into 10 to the power 20 electrons. I think all of you can understand. Now, let us see the second question. An aluminium wire of diameter 0.24 centimeter is connected in series to a copper wire of diameter 0.16 centimeter. The wires carry an electric current of 10 ampere. Both the wires are carrying the same amount of current, mind it. Then determine the current density of aluminum wire. Both are connected in series like this, end to end, and they are asking the current density only in the aluminum wire. Then here the information they have given for copper wire has nothing to do. So we are not interested in this underlying statement. We are interested where? Here, aluminum wire, because the amount of current, and we are going to find from there the current density of aluminum wire. Part 2, diameter of the wire. Diameter, let us write this D. It is 0.24 centimeter. Convert it into meter. This is divided by 100. It is 0.24 in 10 to the power minus 2 meter. But we don't require diameter. Area to find out, we require radius. So we'll divide it by 2. Radius of the wire will be 0.24 into 10 to the power minus 2 divided by 2 meter. This 2, if you divide it, you'll get 0.12 into 10 to the power minus 2 meter. So this is the radius of the aluminum wire. Now, the wires are, both of them are carrying 10 ampere of current. We are talking about aluminum wire now. The current, the aluminum wire is carrying current I is equal to 10 ampere. Then what will be the current density asking? So we know that current density J is equal to the amount of current that flows per unit area, and the area of cross section of the wire is given, diameter is given, means it will be circular. This area of cross section is circular. That's why we could find out the radius. So you will apply the formula for area of circle, that is pi r square. This is the formula for area of circle. Then put the values. Current is 10 ampere. Pi value, as you know, 22 by 7, or you can use 3.14 as well. Then radius square, then this value, radius twice, you do 0.12 into 10 to the power minus 2 into 0.12 into 10 to the power minus 2. Then the next thing, this terms, you can take it up, lift up, arrange it. I'm writing here. So current density J is equal to 10. So I'm writing 10 into 7. This 7 will go up. And here downside you have 22. Then what I'll do is this one 0.12. I'll write only 12. Decimal 2 digits, so multiply by 100. Then again this one 0.12. I'll write here 12. Then here again I'll multiply by 100. Then this 10 power minus 2, 10 power minus 2, lift it up. then it will become 10 power plus 2, 10 power plus 2. Then it will become easy for you to calculate. Now see here, the number, if you look carefully, without 10, 100,000, only 7 is there. I'll write 7 only. 10 power here, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'll write here 9. Divided by 12 into 12 into 22. 12 into 12, if you multiply, you know that it is 144. Multiply by 22, 882, 882, 8, 16, 6, 1 in hand, 10, 11, 1, 1 in hand, 3. So it will come out as 3168. Now, if we divide this 7 by 3168, then first it will come decimal, then 0, then 0, then 0. It is not good to do. What you can do is borrow some 10 from here. 1 0 I am borrowing, it will become 70. Still I cannot divide with this. Again 1 0 I will borrow, it will become 700. Still I cannot divide with this 2168. One more 0 I will borrow, then it will become 3 zeros. Then you can divide by 3168. Then how many zeros you have borrowed? 3. So it will remain how much? 6 here. 3 is borrowed by 7. This is 3168. Now you can divide these two and get the final answer. 7,000 dividing by 3168. Surely 2 times. 8 to 0, 16, 6, 1 in hand. 12, 13, 3, 1 in hand. 2, 3, 2, 3 are 6. Subtract it, 10 minus 6, 4. 9 minus 3 is 6. 9 minus 3 is 6. Again I will put 0. Then I have to put 1 decimal. Again 2 times I can do 6, 3, 3, 6. Then you can stop. After decimal 1 digit if you get, you can stop. 2.2 into 10 to the power 6. And what is the SI unit of current density? If you forget, you can look the formula ampere divided by meter square. So it is called ampere per meter square. Ampere per meter square. This is the calculation part. So this way you can find out the current density. So let us solve this question and see. Question number 3. A silver wire has a resistance of 2.1 ohm at 27.5 degrees Celsius and a resistance of 2.7 ohm at 100 degrees Celsius. Two different temperatures you can see here. Initial and this is final. So let us represent initial with T1. T1 is equal to 27.5 degrees Celsius. At this temperature, resistance, let us take it as R1, is 2.1 ohm. And resistance of 2.7 ohm at 100 degrees Celsius, let us take the final temperature as T2, 100 degrees Celsius. At resistance, the resistance finally it is 2.7 ohm. From here you are asked to find out the temperature coefficient of, they can ask resistance or resistivity, whatever it is given temperature coefficient of resistance. So what we'll do, we know that temperature coefficient of resistance alpha is equal to final resistance minus initial resistance divided by the initial resistance and the change in temperature. So here we write T2 minus T1. Now after writing down the formula, put down the values. R2 it is 2.7 minus R1 is 2.1 divided by R1 is 2.1 into change in temperature 100 minus 27.5. So here units if you use, here it will be ohm. Here also will be ohm, it will get cancelled. Here it will be degree Celsius. So answer will come out in terms of per degree Celsius. Let us calculate it. Subtract it. 0.6 divided by 2.1 into 100 minus 27.5. 5. 9 minus 7 is 2. 9 minus 2 is 7. So it is 72.5 degrees. 72.5. Now remove the decimals and then we'll calculate it. 6 if I write downside, I'll have 10 after decimal one digit, and then down here 21 if I write here 110, and 725 if I write after decimal one digit, so 10 will come. This 10 will get cancelled. So in this case 6 into 10 is 60 divided by 725 into 21. 5, 2, 7, 10, 0, 1 in hand, 4, 5, 14, 5, 2, 12, 2, 1 in hand, 5, 1. 1, 5, 2, 2, 5. This time you cannot borrow any zeros here, so you have to go for direct division. Let us divide this value. 60. We are dividing by 15225. 15225. So cannot divide 0 if I put decimal, and still cannot divide 0 if I put 1 0. Still cannot divide 0 if I put here also 1 0. Now we can divide it. Most probably 15225 3 times will come. 15, 6, 7, 6, 15, 5, 1 in hand, 3, 4. So it will be 3 times. 4, 5, 6, 7, 5, 5, 9 minus 7 is 2, 9 minus 6 is 3, 9 minus 5 is 4, and this is 1. Put 1 0, then yes, 9 times you can take it. It is 137025. Is enough. After this, you can write down its value. In decimal value, if you write 0.0039, the unit of per degree Celsius, you write. And if you write it scientifically more nicely, bring the decimal 1, 2, 3 steps ahead. It will become 3.9 into 10 power. How many steps we have got? 3. So it will be minus 3. Right side if you move, then power will become minus 3 per degree Celsius. This way you can solve. Students, these are not the only question that you need to solve. You have to solve many more questions because you have to face a tougher competitive world. These are just basics that I am showing you that this is the way that you can do. Thank you for watching the video and stay tuned with LFI Educates till the next video comes.